Okay, you guys, holy cow. Gotta push the bottom in. Khadijah, can you read out step number 3? Will you read step 3 for us? No? You have it in yours, don't you? Christian, will you read out step 3 for us?
Yep. Point out that since the assumption leads to contradiction, the original conclusion that we're asked to prove must be true.
Awesome. So we start by saying the opposite. We showed that doesn't work, so that means the original has to be ending up true. So we did one example here. We said that if negative 2x plus 11 is less than 7, then x has to be greater than 2. So we started with the opposite. No. You did it backwards. You can't go from the bathroom to us. You have to go from us to the bathroom. Try again. All right. So if negative 2x plus 11 is less than 7, then x had to be greater than 2. So we started that x is greater than 2, and we did the opposite, which there was only two other options. Either x is equal to 2, or x was less than 2. So we started with x is equal to 2, and then we did numbers less than 2. And did any of those numbers, were any of them less than 7? No. So it doesn't work. So we said, yep, it has to be that x is greater than 2, because this didn't work. All right, here we go with our next example. We're going to start by drawing a triangle. We're going to call this J, K, and L. Okay, Layla, focus. Starting on a new page, so you can come back to that. All right, we know J to K is 8. KL is 5, and JL is 7. All right, what we're trying to prove is that if triangle JKL is as shown, meaning we're trusting that picture, we're not going to list out all the things we know about it in our proof here. But what we're going to try and prove is that the measure of angle K has to be less than the measure of angle L. All right, so for step 1, we need to state the opposite. So for a less than, what are the other options we have other than a number is less than another number? Greater than, or it could be equal to. And in this case, when we deal with a triangle, the greater than and the equal to are really different, so we have to treat those separately. So we're going to call them cases. So we have case 1. And case 2. In case 1, we're going to do that the angle K, measure of angle K, is greater than measure of angle L. So that was one option. What is the only other option we have left that we have to prove is not true? Equal. So measure of angle K is equal to measure of angle L. So there's only 3 options here. So out of the 3 options, if I can show that this doesn't work and this doesn't work, then we know that the only option left, that it's less. Okay, so we're going to go to step 2. Step 2 is our work showing why it won't work. So in step 2, if I know that angle K is bigger than angle L, if I go back to what we did on Monday, when I knew one angle was bigger than the next angle, what did I know about the sides? Yeah, it goes in the same thing, the side opposite. Mubashir, guys, hi, focus. You can do this. All right. So we know it goes in the same order. So if it's a smaller angle, the side across is smaller. If it's a bigger angle, the bigger side is across. So if I know that angle K is bigger, what's the side opposite of angle K? JL is going to have to be bigger than what's the side opposite of angle L? JK. And that's our angle side relationship theorem. But what is JL? What number is JL? 7. Is 7 greater than JK? What is JK? 8. Is 7 bigger than 8? No. So it does not work. So case number 1 for sure, nope, doesn't work. So now what we're left with is either that the angles are equal, or the original that the angle K is less than angle L. Alright, for this one we're going to go way back to chapter 4, aka it's not that far back. Those of you that had us last try can flip back to chapter 4, 4-6 part 2. We know that if two angles are the same, then the sides opposite of them are also the same. Remember, what do we call that triangle when we had two angles that were the same and two sides that are the same? Isosceles. So if two angles are the same, then that means the two sides have to be the same. So in this one, when we say angle K is equal to angle L, we're saying the sides opposite also have to be equal. So what's the side opposite of angle K? JL would have to be the same as, what's the side opposite of L? JK. And that's our converse of the isosceles triangle theorem. Okay, but what is JL? We have the picture. We have to assume the picture was true because it says JKL is as shown. So the hypothesis is still true, the if part. So if this is as shown, does that work? Is JL equal to JK?
No.
No, because what's JL? 7. Does 7 equal JK? No. So it does not work. So because those two options don't work, what's the only option left? The original, that's less than. Okay, so because neither case worked, or neither case above works, we know measure of angle K is less than measure of angle L. Alright, we're going to do one more problem. This one's a little bit more wordy. But this one might be a little bit easier to comprehend because, I don't know. Maybe none of them are easy to comprehend. IDK, man. I just work here. What? Alright. So the second one we're going to prove is that a triangle can have at most one obtuse angle. A triangle can have at most one obtuse angle.
What is an obtuse angle? Bigger than 90. So what we want to prove is that a triangle can't have more than one angle bigger than 90.
So if I draw an obtuse angle, now I want another obtuse angle. Here's like my 90. I'd have to go more than that, so it's going to have to go this way. Out of triangle.
Can we make a triangle like that?
Because in order for it to connect, it's going to have to go less than 90. Yeah, so that's kind of our idea is like, well, try to prove it. Draw a triangle. It doesn't work. Okay? Unless we were on a basketball. Fun fact. When you do it on a sphere, it works. But this one, it doesn't. All right. So, step number 1 is to assume our opposite. So we're going to start by saying assume a triangle. Now this one is a little bit goofy because saying cannot doesn't really work. So if a triangle can have at most one obtuse angle, what would be the opposite angle only being able to have one obtuse angle? Infinite? Well, there's only how many angles though? 3. So it could have, if it's at most 1, our other options is either it could have 2 or 3. Yep. So we could say more than, or we could say 1 or 2. But we're going to say assume a triangle has more than one obtuse angle. All right, so there's our statement. Now we're going to prove why that does not work. What makes that not the case? So in step number 2, I'm going to start by drawing a triangle just so that we have an idea, a reference. And I'm just going to label those numbers 1, or those angles 1, 2, and 3. And we know at least 2 of them are obtuse. Which 2 do you want to be obtuse? Doesn't matter.
2 and 1.
2 and 1? Okay. So we know the measure of angle 1 is bigger than 90 because it's obtuse. And the measure of angle 2 is bigger than 90 because it's obtuse. But what do we know about all triangles and their angles? They have to add up to 180. If I take a number that's bigger than 90 and I add it to a number that's bigger than 90, it's going to be above what? 180. Measure of angle 1 plus measure of angle 2 would have to be greater than 180. Because if this number is bigger than 90 and this number is bigger than 90, when I put them together, they're going to be bigger than 180. And that means if I add in a third angle, no matter what that angle is, it could be obtuse, it doesn't have to be obtuse, it could be acute, whatever it is. When I add in a third number, what's that going to be bigger than? Yeah, it's bigger. If I have a number bigger than 180 and I add more to it, it's still going to be bigger than 180. So step number 3, we have to say why that's a problem. Why is it a problem that the angles add up to more than 180?
Then it wouldn't be a triangle. Right?
Yeah. The triangle angle sum theorem says the 3 angles must add to 180. So by contradiction, by our method in saying that there was a contradiction there, a triangle can only have at most one obtuse angle.